Hey everybody, today is we're going to be working on the intro to the next chapter. So we're going to run through kind of a thought exercises as we introduce the idea of chi-square and what chi-square means and how we use it. So let's talk about M&Ms. Mars & Company makes milk chocolate candies called M&Ms. If you call the Consumer Affairs Department, they will tell you that when they make the M&Ms, on average, candies will contain 13% brown and reds, 14% yellows, 16% greens, 20% oranges, and 24% blues. So let's say we opened up a bag. Let's say we opened up a bag of these candies. You know, here's our bag of candies right here. And we counted them. And we said we got 9 blue, 8 orange, 12 green, 15 red, 15 yellow, 10 red, and 6 brown for 60 total. So my question for you is, what is p hat blue? Well, p hat blue would be 9 out of 60, or around 0.15. So p hat blue. And they said that it's supposed to be 24% blues. Now, does that mean that they're lying about blues? And does that mean that they're lying about the whole thing? And so, of course, we could go through and we could do a one sample null hypothesis, with the hypothesis being, sorry, I had to pause because I had to talk to a student. So we could test our null hypothesis. Hold on, I'm going to pause again because the student didn't close the door. So I could test if this null null hypothesis worked. But this would really only tell me if the blues were correct. It wouldn't tell me anything about p hat orange, or p hat green, or p hat yellow, or p hat red, or p hat brown. And so what we need is we need a new statistic. We need a new way of looking at this, a new way of thinking about it. And so instead of just doing a null hypothesis for one of these, we're going to do a null hypothesis to see if all of them fit. And so we're going to create something known as a chi-square goodness of fit test, which is going to be, and then we'll learn other chi-square tests. So what we're going to do is to take all the colors into consideration. And we're going to look and see if our distribution. And so what we're going to do is we're going to look at, okay, according to them, what is our expected count of each one of these colors? We had a count of colors, right? Here that we saw in our sample. But the company gave us percentages. They said p hat brown was 0.13. P hat red was 0.13. So if I take a sample of 60, then I would expect there to be, on average, and this is why we're going to get decimals here, on average for there to be 7.8 browns and 7.8 reds. And I can do that expected count for each one of those. And so our null hypothesis would be, you know, that the stated color is correct, and the alternative hypothesis is that they are not correct, right? Or we could state it that they're going to hit these, and at least one of them is incorrect. So what we're going to do is we're going to look at the expected counts and compare them to the observed counts. And then we're going to do some math on it and look at it. And in general, the expected counts can be obtained by multiplying the proportion of the population distribution in each category by the sample size. So, for example, so we just did this thing with the milk chocolate, right? And here is that 0.78 and 0.78 I got. So this is, we said p hat blue was 0.24, and 0.24 times 60 gives me 0.24 times 60 gives me this 14.4. And so then we're going to look at, all right, so here is what we would expect to get, and here was what we observed. And the question is, are these differences between these two numbers big enough for me to doubt what Mars was saying? Are these two numbers different enough that that something run amiss? Now, we're not concerned if they're bigger or smaller, just that they are different. So we would take the difference of each one. And in our category, we see some fairly large differences. So how likely is it that we would get those by chance? And so we're going to create a new statistic, and that statistic is the chi-square statistic. It's going to measure how different our observed is from our expected. And if you took AP Bio, you may have seen this already. And so here's the formula we're going to do. We're going to do observed minus expected. We're going to square it. We're going to divide it by expected, and then we're going to add the whole thing up. So for this, right, observed minus expected squared over expected. And we get a number of 2.025. And then for the next one, it would be 8 minus 12 squared over 12. Or 1.33, repeating. And we keep going all the way down, 12 minus 9.6 squared divided by 9.6. 15 minus 8.4 divided by 8.4, and this is squared to make it positive 15. And you would keep going, and then at the end, we would add up all of these values. And so we would add all of those numbers up. And that's going to be our chi-square statistic. 2.025 plus 1.33 plus 0.6 plus 5.19 plus 0.48 plus 0.42. And you get a chi-statistic of about 10.045. They rounded less than I did. They get 10.180. And so then we can compare it to an established chi-square distribution. Now the chi-square distribution is different than the distributions we've seen before. And it's different because if you'll notice, it is most assuredly right skewed. It is not a symmetric. It is definitely not normal. And this is a chi-square with 5 degrees of freedom. And you determine the degrees of freedom. Degrees of freedom is going to be the number of categories minus 1. And the chi-square has a very different shape depending on how many degrees of freedom there are. but it is always right skewed. And once again, degrees of freedom is number of categories minus 1. And so our p-value is, if we go to 5 degrees of freedom in the table in the back of the book, if you go to the back of your book, just like there's a table for t and a table for normal, there is a table for chi-squared. And by the way, I should have said this earlier, this is chi. If you see it, this cursive x is called chi, so this is chi-squared. And because my value falls between these two values, that means our p-value is between 0.05 and 0.01. We didn't establish an alpha, so we'll use 0.05. So we would fail to reject the null hypothesis. We do not have sufficient evidence to conclude that the company's claimed color distribution is incorrect. So what we're going to be doing in class is we're going to be looking at this chi-squared and practicing it. So we are going to be really messing with this chi-squared. And we'll be talking about how you set up the null and how everything goes. But the key thing is where this comes from. And so it's this formula. You do it for each one of them and put it up. And then I'm going to show you how to do it in the calculator, which is significantly easier. So that's it for today. Today's video. See you in class.